So, and Megan, you can start sharing your screen if you'd like.
Okay. Is that sharing?
Yeah, we see presentation view now. First slide.
Perfect.
All right, so I think we're good to get started. So today I'd like to welcome Dr. Megan Gillies from the University of Calgary, who will be talking about optical field line resonances today. Megan is an expert in ionospheric science and works closely with data from the SuperDARN radars as well as ground-based all-sky imagers. She received her PhD in 2015 from the University of Saskatchewan, studying global-scale observations of convection during enhanced solar wind and geomagnetic activity. Currently, Megan is a researcher with the Aurora group at the University of Calgary, focusing on auroral studies and the calibration of the auroral instrumentation and all-sky imagers at the University of Calgary. She is presently creating the definitive and final multi-decade calibrated historical MSP data set, the meridian scanning photometers, and overseeing the calibration of the ASIs and development of SkyMap files, which allow for the quantitative analysis of the auroral data sets, which Megan will be talking about today. So with that, Megan, if you'd like to take it away.
Awesome. Thank you very much, Kyle. So, good morning. My name is Megan Gillis, and as Kyle mentioned, I am currently a researcher at the University of Calgary. I work predominantly with the optical all-sky imagers, like the Themis and Rigo ground-based imagers, and I use them in conjunction with other instruments to study the aurora. Now, one of the auroral morphologies I find particularly fascinating is a type of periodic auroral arc known as optical field line resonance. So I'd just like to thank everyone here for coming and Kyle for the invitation to come and talk about one of my favorite types of auroral arcs. So here's a brief overview of what I'd like to talk about today. So the first thing is to just briefly try to explain what a field line resonance is for those who might not be familiar with the topic. And then I'm going to talk about some past studies which looked at generation mechanisms and models on how field line resonances occur in the magnetosphere and some of these questions that have arisen from some of those studies. And then we're going to talk about optical field line resonance arcs. We're going to look at some of the original studies done by past researchers, look at a case study I'm working on, and then take a look at the statistics of this particular type of auroral morphology. And then finally, how we can actually use field line resonance arcs to contribute to the discussion about field line resonances in the magnetosphere. Before I start, I just want to clarify that the references I'm using in this overview are not an extensive list at all, but just a small sample of the incredible amount of work that people have done on this subject. So where to start? Well, here's a standard picture that will be familiar to a lot of people here. This is the Earth's magnetosphere. This is the region of space around the Earth that is actually dominated by our magnetic field. Now, if we were by ourselves in space, the shape of our magnetic field would resemble that of a magnetic dipole. However, we are highly influenced by the presence of our sun and the solar wind that streams away from it. Now, the overall shape of what we call our magnetosphere highly resembles that of a windsock, and its shape varies quite a bit with solar wind activity. Now, when the solar wind is more active, the front portion can become very squished and the tail portion incredibly elongated. Now, associated with all these magnetic fields are a huge system of currents and electric fields which drive some of the forces which cause the aurora. Now, the end result of our magnetosphere is a system of these closed magnetic field lines, or a magnetospheric cavity, if you will, that works as a shield to protect us from the sun's energetic particles. And even though we are directly shielded from the solar wind, various processes happen which allow transfer of energy and particles from that solar wind into our magnetospheric system. Now, one example of that, sometimes the solar wind can contain pressure oscillations, which can then set up magnetosonic waves in the magnetosphere. Now, when these waves occur in our magnetosphere, they can sometimes create standing waves, which we call resonant waves. Now, a great example of a standing wave and resonance, which most people will recognize, comes from music created by stringed instruments, particularly ones like a guitar or a violin. Now, the note created when you strum a guitar is the result of a vibration along the string, creating a standing wave resonating at a certain frequency. It's basically back to first-year physics. Now, when you pluck a guitar string, a traveling wave forms, and here we see it in red moving along to the right of the screen. It travels along the length of the string until it reaches the fixed end, at which point the wave is reflected back, which we see here by the blue traveling wave going to the left of the screen. Now, if the wavelength of the reflected wave is the same as the original wave, constructive interference will occur and a standing wave or resonance occurs. Even though the original wave and the reflected wave are moving and traveling opposite directions, superposition of the waves looks like they're not moving at all. And the standing wave here is the one that's just sort of oscillating up and down in green. Now, the frequencies or notes created by this standing wave are restricted by a combination of how long the string is, what the string density is, and how fast the wave travels. If you consider something like a mandolin, for example, it has a higher pitch than a guitar, or higher frequencies, because it has shorter strings, so the waves need to move faster along it. By changing where along the bridge of the guitar you compress the string, you can change the mode of the wave, or the harmonic, and thus the sound. In this example here, there are about 4 antinodes, so I believe that's playing the 4th harmonic. Now, in the case of the guitar, the waves cause a vibration which disturbs the air around the string. And the oscillation of the air is amplified by that hollow chamber behind the chamber of the guitar, and that amplifies the sort of sound that we hear. Now, how does this relate back to the magnetosphere? Well, if you imagine that the magnetosphere is like that guitar, the ends of the string can be tethered in the north and southern parts of the ionosphere. And you can relate those traveling waves up and down the field line, transporting energy along it, to basically the standing wave of the guitar. Now, a geomagnetic field line isn't the same as a string, obviously. When we tend to draw magnetic field lines like strings, they're more of an abstract representation of the flux tubes tied to lines of geomagnetic force. So despite that, though, a magnetic field line kind of behaves in the same way. The little inset is a figure from Kufko and Russell's Introduction to Space Plasma book, and it shows how those field lines mimic those of that standing wave. A nice way to think about it is that field line resonances are the Earth's way of making music. So let's talk about these oscillations in the magnetic field. So early observations of these perturbations have long been observed by ground-based magnetometers dating all the way back to the 1950s. These particular perturbations have long periods between 1 and 10 minutes, and were described by Dungy in 1955 as a signature of transverse oscillations of the dipole-like magnetic field, or magnetic flux tubes. So when people considered the idea that the ionosphere acted as a tether at either end of the flux tube, a resonance or a standing wave was an explanation for the perturbations that were being observed by the ground-based magnetometers. When considering that distance along a magnetic field line from southern to northern hemisphere, compressional waves triggered by this oscillation could create an energy source which is coupled to the magnetosphere. Now, when we play a guitar, those compressional waves are triggered by, us strumming the strings on the guitar. But how does this happen in the magnetosphere? Well, the common thought is that the compressional waves occur from the formation of Kelvin-Helmholtz instabilities along the magnetopause. This Kelvin-Helmholtz instability causes a perturbation in the magnetospheric cavity, which in turn creates a compressional wave that causes the field line to move. If the field line is the right length, or the speed of the wave is the right speed, resonance can actually occur. Now, with this scenario in mind, the idea of natural frequencies emerging from these oscillations, very similar to how notes on a guitar form, emerged and became quite prominent when discussing generation energy transport theories. The resonant theory was a great explanation to explain the variation in amplitude as a function of latitude and frequency changes. So when describing field line resonances, one parameter that tends to come up a lot is something called the wave number. Now, the magnitude of the wave number gives information on the polarization of the standing wave. So this example here, which I have adapted from one of Ian Mann's papers, shows a toroidal wave. And this type of wave has the magnetic field oscillations confined into the azimuthal direction. This sets up oscillations of the electric field in the radial direction. And because of the amplitude of is large in the azimuthal direction, the wave number is quite small. Colloidal waves, on the other hand, have the magnetic field oscillations confined to the radial direction. If you imagine this sort of dashed line as a sun to tail meridian, you can see the compressional waves, either the front or the tail of the magnetosphere, would cause radial motion in the field line. And in this case, the magnetic field oscillates radially and the electric field oscillates azimuthally. And since the motion of the field line is predominantly radial, the azimuthal amplitude of the wave is rather small, and therefore the azimuthal wave number can be somewhat large. Looking at this wave number of FLR can give some information on what type of wave polarization it is, and in turn, where in our system they tend to be forming. So let's take a quick look at some of the past research that has been done looking at the frequencies of the field line resonance and some of the theories on their generation. So one of the original theories considered the compressional waves caused by those Kelvin-Helmholtz instabilities along the magnetosheath to be one of the main causes of those field line resonances. Now, these compressional waves, which cause the oscillation of the magnetic flux tubes, would create a constant low power in the magnetosphere, which will allow for all resonant frequencies to kind of occur. In essence, the magnetic field topology is constantly changing with changes in the solar wind. As the field line or the solar wind increases and decreases, the field lines compress, expand, lengthen, and shorten. Like the guitar analogy, changing the length of the string or the properties of the field line, changes in solar wind will change the note or the resonance of the field line, allowing for this wide range of frequencies to be observed. Despite this idea, observations seem to indicate that there were dominant frequencies present. So in 1985, Margaret Kivelson and David Southwood published a study that suggested a box model of the magnetosphere that was predicted to yield damp, fast eigenmode solutions with these quantized frequencies. Now, they set out and elaborated on this theory in this particular paper, which described their model, and this would become one of the cornerstone foundation theories used to describe field line resonance in the magnetosphere. And what was particularly important about this model was the notion that if the magnetospheric cavity was excited by a broadband source, for example, an external impulse, then the field line resonances whose resonant frequencies matched a global frequency were the most likely to be excited and of course seen. Now, John Sampson went a step further and quantized what these natural frequencies were. Using an HF radar, Sampson performed a study of F-region drifts associated with field line resonances in our magnetosphere. And from this survey, he determined that these resonances were seen predominantly between local midnight and morning. And one of the major findings of this study was what became known as the magic frequencies, or a preference for discrete latitude-dependent frequencies at approximately 1.3, 1.9, 2.6 to 2.7, and 3.2 to 3.4 millihertz. Also important is that he showed that these frequencies were actually consistent with an MHD waveguide model, where the magnetic field, where the wave propagates along these dipole field lines, and it's actually reflected at the magnetopods. Now, what was significant about Kivelson and Southwood's theory, which was used by Sampson and subsequently other researchers, was that these discrete frequencies were a direct result of using the magnetosphere as a global cavity. This is very similar to that sounding box on the guitar we talked about earlier. The magnetosphere itself is presumed to resonate globally at the frequencies determined by the size, shape, mass density, and field topology, right? Basically, a sort of a self-contained system almost. Now, in 2002, Larry Kufko decided to look at the solar wind as a possible generator for these resonant waves. And this is a figure from his study. It was really neat. He looked at magnetic data at geosynchronous orbit, so approximately 6.6 RE. That's well within the magnetosphere. And he looked at the upstream solar wind from the wind satellite. So this image here is from figure 2 of that paper. Taking the Fourier transform of data from these two positions, Larry actually found significant power at frequencies of 0.7, 1.4, 2.0, and 2.7 millihertz. In this study, the wind data has been shifted by 17 minutes to account for propagation effects. Now, Kufko and his team showed in this study that the upstream solar wind density and dynamic pressure variations preceded the compressional magnetic field variations at geosynchronous orbit. Not only that, they also showed that the same discrete frequencies found in the solar wind were being seen in the magnetosphere. Oops. Their major conclusions suggested that instead of the cavity mode theory, it was density oscillations present in the solar wind, which were actually driving the discrete ultra-low frequency perturbations in the magnetosphere, at least sometimes. So basically more of an outside-in effect, contrary to what theory was at the time. Now, in 2003, Greg Baker from the University of Calgary performed an extensive study to quantify a couple of parameters of ground-based pulsations in that 3 to 5 minute range. So officially kind of classed as something called PC5 pulsations, and using the Canopus magnetometers. Now, Baker surveyed 10 years of Canopus magnetometer data, and he cataloged over 4,500 hours of pulsation activity. Now, from the survey, they're actually able to determine a lot of important results. And the first I've highlighted here is important when we're discussing optical signatures later. Now, one of the results was the verification of a known asymmetry in the occurrence distribution of pulsations where pulsations with field line resonant characteristics have a strong preference for dawn over dusk distributions. Now, another important result of the study is shown here in the figure on the right. And this is a stack plot of the frequencies of the field line resonances and the non-field line resonance PC5 pulsations. Focusing on the middle panel, which specifically looks at field line resonances, we see something interesting. There appears to be a continuous distribution of stable, recurring, discrete pulsation frequencies. Now, this is almost the opposite of what had been seen before with respect to those magic frequencies proposed by John Sampson. I believe these particular vertical lines are there to illustrate where the magic frequencies would have been seen. In 2003, Jonathan Ray and his team published an incredible study which looked at the magnetic field resonances from multiple instruments from the solar wind all the way down to the ground. In the bottom right corner here, you can see where the in situ observations are. And at the time, cluster was near the magnetopause, GOES 10, Polar and Langle were all near geosynchronous orbit. And there was also solar wind data available from ACE Wind and the GeoTails satellites. Now, the picture on the left here shows a stacked plot of the analysis of data from these various instruments from the ground all the way into space, from the bottom to the top. The bottom panel is the magnetometer data from the Gillies location, or Fourier transform it. Data from the Prince George and Saskatoon Superdarn radars, which looked at convection around 250 kilometers altitude, is right here. And it's a really nice sampling of a column of data from the ground up. Now, the important thing to get from this plot is that from the magnetopause down, so roughly here down, there's a common frequency observed. And from the top panel, we can see that this frequency is not observed in the solar wind. Now, they concluded that the most likely explanation is that the magnetopause oscillations couple energy to field lines close to the location of where polar was. And that sets up a standing alphane wave along the resonant field lines, which are then observed in the ionosphere and by magnetometers on the ground. In the absence of a monochromatic dynamic pressure variation in the solar wind, this event is a potential example where discrete frequency pulsations in the magnetosphere result from the excitation of a magnetospheric waveguide mode, perhaps excited via that Kelvin-Helmholtz instability or via overreflection at the dust side magnetopause. So some of the questions that have arisen from these studies are there actually magic frequencies in the pulsations, in the field line resonances? Do the continually changing magnetic field topology allow for all resonant frequencies? Do the resonances form as a result of resonance of the magnetospheric cavity, or do the resonances come from the solar wind and are transferred into the magnetosphere? So what do field line resonances have to do with the aurora, and specifically with auroral arcs? Well, one kind of well-known feature that occurs along closed magnetic field lines happens to be the aurora. The aurora is a phenomenon that is generally tied to these magnetic field lines, so if the field lines are resonating, what effect, if anything, does this have on the aurora? So what do I mean when I talk about field line resonant arcs? This movie playing on the left here is a really good example. This clip was actually created using data from one of the RIGO or Redline all-sky imagers. This camera has an exposure time of 2 seconds with a 3-second cadence. It is specifically filtered for the 630 nanometer wavelength auroral emission, and this allows for observations of redline auroral emissions. I believe there are currently 9 cameras stationed across Canada and the Canadian North. Aside from their unique filtering, these cameras have been calibrated and are capable of producing a data product with luminosity values in units of Rayleighs, which is really awesome. In this video, north is at the top and south is at the bottom. If you watch this video loop through, what I want you to focus on is the fact that there is an arc. It appears at a certain point, roughly around this point in the camera, and it slowly travels northward and then dissipates. While it's doing that, another arc reappears near its original position and follows the same path. And this oscillation is repeated over and over. This particular behavior pattern is what we associate with the field line resonant arcs. So how do we identify these optical field line resonances in the data? Simplest approach is to actually use a keyogram. So the panel on the right is a data product called a keyogram for those who may not be familiar with it. Now they are just a north-south section of one of these images, and then they're stacked in time. This particular keyogram shows a field line resonant arc system which remains somewhat stable over the course of 1 hour. The smooth banded lines of long-lived, slowly moving auroral arcs beginning at lower latitudes and propagating northward are the signature of this type of periodic arc. Subsequent arcs in the system appear near the initial arc latitude, and they all kind of follow the similar path until the system kind of quits. Now, how do you determine if these are just a steady multiple arc system or a true optical representation of magnetic field line resonances? So some of the key instruments in looking at magnetospheric field line resonance are those in situ satellite data, geosynchronous, the F-region drift seen at similar altitudes to Aurora using things like the Superdarn radar, or ground-based magnetometers. So sometimes there aren't in situ satellite measurements that can be connected to these arcs, but magnetometers are running all the time. And the field line resonances can sometimes be seen by these ground-based magnetometers. So how do these arc systems compare to what the magnetometers see? Now, to show you, I have picked one event where there are two distinctly different field line resonant arc systems, and we've identified them using the RIGO all-sky imagers. And this particular one was from Gillies, Manitoba. And we compare the arcs to what we see from the magnetometers. Now, in this keyogram, we actually are looking at two separate arc systems. And in this panel, I'm showing the X component of the geomagnetic field from a collocated magnetometer. Now, after performing a Fourier analysis on the optical data and the magnetometer data, we can see marked similarities between the two data sets. So let's first look at this particular system, the first system. The black line represents the results of our Fourier analysis on the magnetometer data. From this, we can see that there's peak frequency of around 6 minutes. The same analysis is performed on the optics and illustrated by the red line. And we see that the arcs also seem to have this preferred periodicity of around 6 minutes as well. When you consider the second arc system, we can again see that similar periodicities between the magnetometer and the all-sky imaging data sets, with the peak period being roughly 8 minutes this time. The slightly longer period of the second system actually reflects field line behavior frequently seen by the magnetometers. Now, the second system is a slightly higher latitude, and that is reflected in the slightly longer period. Similarities between the magnetometer frequencies and the optical data actually implies a correlation between field line resonances and these particular arc systems. Now, field line resonant auroral arcs are not new to the scientific community. They have been identified before, but they're not actually seen very often. I can think of about 10 or so examples of field line resonances in the literature, which makes it very difficult to model when there are so few of these examples. Now, John Sampson, Steve Milan, Robert Rankin are some of the scientists who apply field line resonance theory to model some of these arcs with really good success. When these standing shear Alfvén waves occur along a field line, they set up a field line current system, and electric field systems are consistent with those found in auroral arcs. When looking at the observations of spatial temporal evolution of the optical signature of these auroral arcs and comparing them to model current systems, there is really good agreement. This image on the right is from 2001, and Steve Milan used field line resonance perturbation theory in this work to model the current systems associated with the resonances. And among other things, this paper looks at modeling the field line currents in the regions associated with the field line resonances. In particular is this figure here on the bottom, which looks at the cross-section of the model currents. And his model suggests that when you see the negative field line currents in these particular kind of hashed bays there, you would be able to see auroral arcs. And of course, when you have positive currents, you wouldn't see them. And this is very similar to what we would see in the data with auroral arc, nothing, auroral arc. This 2003 study by John Sampson and his team also uses field line resonance theories to model the auroral arcs as well. Now, this image here in the lower right is a temporal, and X depends of the amplitude of the parallel electric current above the ionosphere. And as you can see, this figure is actually rotated from the paper by 90 degrees because the pole forward sort of at the top. And you can see that the resulting model is actually very similar to what you would see from the data. Now, in order to model something, it's really helpful to have as much information as possible to constrain the parameters that you're using. Now, historically, this pattern of auroral arc motion comes up, but again, not very often. Now, although the field line resonant models are capable of reproducing many of the characteristics of these periodic arcs, more information is needed to constrain the models and align them to a bit more with observations. Now, multipoint studies or data cube studies are really helpful in providing as much information as possible about these systems. So this multipoint study by Lisa Badley and her team from 2017 is amazing. This is an exciting look at data from an equator-word field line resonance system. Now, to me, there were two really interesting things about the study. The first one, and it's not shown in this image, was that there was actually no direct magnetic signature of the wave of this particular field line resonant arc system seen in the ground-based magnetometers. There was field line resonance frequencies seeing a little bit northward of this, but not at the same frequency seen in the optics. And when you're thinking about that chain of events from the magnetosphere down to the ground, like in the Jonathan Ray study, this is a bit of a disconnect and really kind of neat. The other thing is what I really find unusual about this event, and that is the other images I've shown you always have this sort of poleward progression of these arcs. In Lisa's study, there is actually equatorward progression of these arcs instead. She found that there was, again, equator motion of the arcs, there was sunward propagation, and it had actually a high azimuthal wave number. Now, if you remember from a couple slides ago, we were talking about wave numbers and what that means. It kind of makes this more of a leaning towards a poloidal mode standing wave instead of one that happens along the flanks. Now, this suggests for this event, at least, that the energy source is actually internal to the Earth's magnetosphere, but it's most likely from a compressional wave emanating from the magnetotail with an earthward propagation. It's kind of really neat. Now, these multi-point studies like Jonathan Ray and Lisa Badley's, which look at various places along a field line resonance, are really important to answer questions regarding about how these arcs form and their connection to the magnetospheric system. They are important for providing observations to constrain the models and can hopefully be used in the modeling community when looking at how auroral arcs driven by ultra-low frequency waves relate to an energy source driver, internal or maybe external to the magnetosphere. The next couple of slides are a quick look at one study that we are currently working on, which investigates the connection of these field line resonance arcs and the Kelvin-Helmholtz instability along the magnetosheath. Now, the image here on the right is from a web interface called Swarm Aurora, which is a fantastic data portal that allows you to quickly see sort of what in situ measurements or what in situ instruments are in conjunction with a ground-based auroral imager when it's on and taking data. If you aren't familiar with the site, I highly suggest taking a look. It is so handy when you're actually doing event studies. Anyway, on this particular day, this is one of those kiograms from RIGO. And we can see the field line resonance style arcs in the kilogram at Fort Smith. Now, in conjunction with the red line images, we can see that these this particular event has an overflight of one of the swarm satellites, in particular it's a swarm B, and at the time has magnetomeron, so we're getting field aligned current measurements, but we also have electric field instrument data. So we have electric field measurements during this event. We also have the footprint of Themis E and D over the field of view of these arcs. When we look a little bit closer at where Themis E and D are, we can see from this image here that they are positioned along the dawn side of the magnetospheric boundary. Now, on the right here, we have actually, again, that periodic field line resonance seen in the kilograms, which are on the ground. But what is really neat is that we can see from the Themis data a matching oscillation and a similar cadence to what we see in the ionosphere. So we can actually learn quite a bit about, quite a bit of information from Themis based upon its position. Now, these figures were created by Francis Fenrich from the University of Alberta in a 2006 study by Hasegawa and his team. They outlined a technique to identify rolled up Kelvin-Helmholtz vortices at the flank magnetopause. And we are currently using that technique found in this paper to suggest that in our event, there is actually a Kelvin-Helmholtz instability along the Magnetosphere sheath on the dawn side. Now, the figure on the left here is a scatter plot in which the x-component of the flow velocity is plotted as a function of ion density. Now, according to Hasegawa's study, this low density and faster than sheath feature is actually indicative of a rolled up Kelvin-Helmholtz instability vortex. Now, the hologram plot on the right shows a nice clockwise rotation of that velocity vector consistent with a clockwise Kelvin-Helmholtz instability vortex on that dawn flank. Now, Frances also looked at HF radar echoes from superdawn during this time period, and she found ionospheric perturbations corresponding to similar pulsation periods as the auroral arcs, roughly about 5-minute periodicity. The event also included that swarm overflight of the arc system, which allowed for electric and magnetic field observations, which we can then use to compare to all those theories. Now, as an example, if you wanted to use the electric field and magnetic field measurements, you can actually calculate the pointing flux along the polar boundary of these periodic arcs. A downward pointing flux could suggest a magnetospheric driver for the field line resonances. Now, recent missions provide an opportunity for rigorous testing of models with the opportunities to couple these ground-based in situ and magnetospheric measurements. And this provides one of those true data cubes for a comprehensive image of what's going on with this type of auroral feature. We can take case studies like this one, Jonathan Ray and Lisa Badley's, and use it to compare it to the models. Now, as I mentioned before, there aren't a lot of this particular type of auroral event recorded in the literature. Now, if field line resonance, though, are so common, why aren't we seeing them more often in the aurora? Personally believe that the lack of events wasn't necessarily because they weren't there. It's just that we were not necessarily looking at the right place, or turns out more specifically, we weren't looking at the right wavelength. Now, what do I mean by this? So prior to the deployment of the Regal all-sky imagers in 2014, we were reliant on things like the Themis white light imagers for observations or meridian scanning photometers, which slightly different. Yeah. Now, the Themis all-sky imagers are incredible cameras. However, the panchromatic images they see are usually dominated by bright, high-energy activity. Now, this is fantastic when you want to study auroral arcs, pulsating aurora, substorm onsets, but it's a little bit more problematic when you're wanting to look at relatively dim features because they get overshadowed. So on this slide, I'm showing the same hour of data. Top panel shows a Themis white light heogram, which is comprised of all those images. And the bottom shows the red line, or the RIGO, or the red line images. Now, because the Themis imagers record all luminosity we see, we can actually see a lot of features in this heogram. We can see clouds, we can see diffuse aurora, we can see strong pulsating patches, and we can still see a little bit of that field line resonance feature in the background. Now, I chose this particular event to show because you can actually still see the field line resonance arcs in sort of the background of the white light images. However, this is not always usually the case. Sometimes if you have a lot of activity going on, the brighter features will completely dominate and you won't actually see them. Now, the bottom panel, which looks specifically at that red line aurora, is a lot clearer. It filters out that high energy stuff, leaving the clear signature of the field line resonance periodic arcs. Now, using instruments tuned to pick out this component of the arc allows us to identify more of this type of auroral morphology. Now, using the red line images from the RIGO array, we set out about looking at identifying as many of this type of arc system as we could find. At the time of this study, we looked at approximately 2 years of red line imaging data, and keeping in mind that a large majority of the red line cameras do not operate in the summer months, we've still found nearly 440 clear usable events. It's quite a few events. In order to easily identify this type of arc, you really need to be able to use the right instrument that wasn't really available on the scope before. When we look at the occurrence distribution of these events, we can actually see that they are very different than typical discrete auroral arcs, In this plot, I'm comparing the occurrence rate as a function of magnetic local time of your typical sort of red line auroral arcs, such as non-periodic single and multiple arcs, to that of the field line resonance periodic arcs. Now, as you can see, the regular arcs are shown in blue, peak in occurrence just before midnight, dropping off dramatically as you approach dawn. Now, the distribution of field line resonance arcs, which is what we see in the red cross-hatched bins, are more likely going to be found in the hours leading up to dawn or around dusk. Now, you can also see here there's an interesting asymmetry seen where there seemed to be a preference for sort of a dawn sort of occurrence. Now, if you remember from the beginning of the talk, this asymmetry in the occurrence distribution of the field line resonant period arcs may look a little bit familiar. A similar dawn and dusk asymmetry was actually seen in Greg Baker's work using the magnetometers to identify field line resonances associated with those PC5 pulsations he was looking at. I'm just placing this little insert here of his result right here just to compare. Now, this is actually really nice confirmation that the periodic arcs we are actually seeing are indeed related with these magnetospheric field line resonances. Now, despite this increasing event, statistically speaking, field line resonant arcs are still somewhat rare. Just to further compare this type of arc system, let's take a look at the comparison between them and common auroral features. And to do so, we're going to look at this little cartoon here. So here we have dawn on the right, noon towards the top at 12 MLT, dusk towards the left and 18 MLT, and midnight towards the bottom of this little polar plot dial. Now, as we saw before, field line resonances tend to occur in this sort of dusk and dawn area. Now, when we looked through all of the events, we found that they aren't that common and they only occur in about 5% of RIGO's viewing data. They're actually dim compared to, say, the green auroral arcs that we normally see, and their occurrence distribution is also unique when we consider standard forms of aurora, such as multiple arc systems and single arc systems. So to provide some context with respect to the different arc morphologies, single and multiple arc systems tend to be the most frequent, and they actually tend to be bright, and they tend to occur towards magnetic midnight, and they make up the bulk of what we would consider auroral observations when we're looking through the data. Pulsating aurora occurs in about 30% or more of them as all-sky imaging auroral observations, around 30% here, and they actually increase in their frequency as you go towards noon. Now, they occur sometimes with other auroral morphologies or on its own, but they tend to appear in this area here. Again, kind of different from our field line resonances. Diffuse aurora is also more common in the post-midnight sector and extending into the noon sector, but can also be seen in general all over the auroral oval. What we can see from this is that field line resonance arcs are just one piece of this massive system. So with this new data set and the ever-evolving opportunity for new instrumentation available to study this auroral form, we hope we can use it to contribute to the modeling community. Detailed studies of lists like the ones that we have created here could help constrain some of the models we talked about earlier. We're hoping to use this data set to perform comprehensive studies of these arcs and how they actually connect to the solar wind, perhaps help answer some of the questions that we talked about earlier. If you'd like to know more about the modeling and some of the observations of this type of arc, please check out this collection. Recently, the International Space Science Institute published this new collection of auroral physics review papers to highlight the progress made in auroral research in the last 2 decades or so since the original Aurora Plasma Physics collection was published in 2002. Now, one of the articles in this collection was written by Robert Rankin, and it goes over a lot of what I've discussed here with a high emphasis on the modeling. It's a really great paper and part of a wonderful collection, so if you have time, I would highly suggest it. Some of the references that I've used today, again, not inclusive of the massive amount of work that's available in the community, just kind of the ones that I sort of pick out to look at. And thank you. That would be it.
You
Kyle,
may be muted, Kyle.
Kyle, you're muted.
Sorry. Thank you for a wonderful talk, Megan. I think that was really great. I really like your animation at the end about the different auroral forms and where we observe them. It reminded me of the wave one that we see. And it's nice to have something similar that you can link between the auroral and the waves we see in space. So I'll encourage anyone to ask their questions in chat right now. I have a couple that I'd like to ask quickly. In one of the initial events that you showed in your study, you saw 2 different periods. Do you have any idea where those two, like why the period would switch in the FLR?
Why they switch from a magnetosphere point of view? I have no idea. Like we kind of went with the idea of, because it's like a slightly higher latitude, that field line length was a little bit longer, and that accounted for why one of them was a little bit shorter than the other one.
Hmm.
But I would have no idea what would happen from a magnetosphere point of view, which would cause that. And systems like that, where there's two sort of oscillations kind of occurring at the same time, I don't see very often. Usually you can have one system going.
Yeah.
So I'm not actually sure if that two system was a transition of something. Like we didn't actually look at solar wind data for this. So was there, this is kind of like goes back to sort of Larry Kufko's idea of solar wind sort of stuff having an effect. So did a frequency there change and propagate in? Were there actually some sort of two weird magnetospheric sort of frequencies happening, or was it just a transition? And I actually, it's something to look into further. And this is what I'm hoping that sort of data set will allow us to do.
Ah, cool. We have a question from Jason Durr. He's wondering, can you determine anything regarding the conductivity by comparing the observed field line resonances and the currents thought to create them?
Yeah, so actually, if you look at Frances Fenrich's work using SuperDarn, she actually redoes a lot of conductivity stuff using, I believe, SuperDarn. And we should be able to back out things like when we look at, so that swarm overpass, we should be able to use the electric field instrument on there to actually back out some of the Peterson and Hall conductivities from there and take a look at how those kind of relate to the arcs. The only downside with that is that the electric field instrument on swarm is not operating all the time. So that type of observation for actual measurements is kind of rare. That being said, we now have this data set, which we have since had expanded from that 440 up to, I think, nearly 800 of these events now. And so when there's time, it's a really good idea to go back and kind of look for conjunction events so that you can actually see when the EFI is on and over one of these events, and then take a look at things like conductivities.
Yeah, cool.
Which would be really fun to do.
Yeah. So Martin Archer has a question. So he says it's really interesting work, and he's wondering about their location of the FLRs that you see. Do you observe them close to the open-closed field line boundary, or are they more deeper in the inner magnetosphere?
At the moment, the ones that we're using are deeper into the magnetosphere. So I always ascribe latitudes associated with like Rankin Inlet and such to be closer to that open-closed boundary. And while there are field line resonances closer to there, like I do see some at the latitudes where Rankin Inlet is, most of my event set is sort of in the middle. It's definitely sort of looking to magnetospheric stuff versus closer to either of the boundaries. That being said, it depends, of course, how the boundary also moves. And we didn't actually look at things like the red line shelf or anything to see if there is compression of the boundary closer to those sort of mid-latitude field line resonances yet. And that is a really good study to kind of look at.
So I have a follow-up regarding the asymmetry, and this might come back to the database. Do you see different propagation directions on the dusk compared to the dawn,
So we
and
actually,
whether moving up in latitude or down in latitude?
so we haven't looked at that yet. That is definitely the next stage of that study, is to look for propagation anti-sunward, see how the latitude of these arcs kind of changes as a function of this as well. And this will actually be able to kind of tell us a lot about like the wave number, and then we're going to be able to kind of like see if any of those ones are like that idea of the poloidal polarization, or if they're all kind of closer to this toroidal motion. And that is very much one of the next steps for this sort of work. And I think an important one, because it'll tell us quite a bit. It'll tell us quite a bit more,
Yeah.
which is always useful.
So we have one last question from Antonova. She's wondering, the corona aurora, are they produced similarly to FLRs? Antonova, if you want to clarify your question, you can come off mute.
I wonder the interest. I am very interested in the mechanism of coronal aurora production. Is it connected with field resonance, or it's necessary to have another explanation of its formation? the connection of these two phenomena, corona aurora and field-line resonance. Do you think something about this?
So when you're describing corona aurora, do you mean like what happens with an onset? I'm not familiar entirely with
corona as a phenomena of aurora formation, typical phenomena of aurora observation, corona. And is it connected with this resonance or not? What do you think?
So I honestly don't have a really good answer. Like for corona aurora, you're going to have electron precipitation in, and field line resonances, you're also going to have precipitation inward as well, set up by the sort of field line current systems. Now, the structures of the field line resonance arcs, when you look at the current sheet sort of orientation similar to Steve Milan's paper, they're very, very structured. And I think coronal or coronal aurora is not as structured in the field, in like the current systems that create it. Not spent a lot of time looking at that type of system, so I don't really have a really good answer. So
circle. I see your point of view.
All right. Well, thank you, Megan. I guess I have one more question. Do you guys have the database available if other people want to dig into it? Is it on this new Aurora pages, the new Swarm Aurora that you have, or?
Yes, which is so handy. So the thing I really like about Swarm Aurora is that you can actually, so I think there's 2 databases right now, Tushy Substorm onset sort of datasets there, and I believe the ARC one is as well. And what's really cool about that is you can just flip through each event and it will show what's available at the time. So data cube like conjunction studies are so much easier to find. Like the one I was presenting here took so much time to like find, and then now it's just like oh okay yeah, and then you sort of flip through and you're like oh we're gonna find so many more of these, and like having the data set published like that really enables people to kind of go through my data set and go yeah that's not one, or oh yeah that's one, and it'll help winnow it down from as we learn more and more about it, which is also super handy. So I totally recommend everyone checking out the site. And the nice thing about that site as well is you don't have to look at my data set. If you have a data set of your own and you're looking for things to do conjunction studies with, you can actually upload your own data set and use them to flip through. At least I'm pretty sure that's a feature that is potentially working right now, and if not, it should be. So it's really handy. I love it. And it's really great because it ties it to the optics. So it only will show you data if there's data available. If there isn't any like ground-based optics associated with it, you just keep going. And it's a really quick way to check through summary stuff. Like with the Swarm EFI not being on all the time, it's really frustrating to spend all that time looking for a conjunction, looking for the ground-based, going, oh my gosh, yes, this has stuff, and then finding out that the overflight doesn't have any data. And it's like a common frustration, I think, in our field where it's like, it's so time-consuming. And Swarm Aurora really helps with that. So I love it. It's fantastic. It's going to change completely how I do my research.
Excellent. That's great to hear. So I'll encourage everyone to go to Swarm Aurora and check it out. And I want to thank you again, Megan. This was a really great talk. Thank you for joining us today. Our next seminar is next week. We're going to have our first set of early career seminars. And we're going to have Riley Troyer from the University of Iowa and Leon Oliver from the University of Alberta. And so we're looking forward to starting the early career seminars this year. They'll be the first Monday of every month, starting February and moving on. And so we hope to see everyone next week. And again, thank you so much, Megan.
Thanks again.
Have a wonderful week, everyone.
Yep, wonderful presentation. Bye-bye.